It's easy to generate histograms with the histC function. The one required argument x is set equal to a variable to be analyzed. The variable you want to analyze should be interval level. If the variable is nominal or ordinal level, you want to use the freqC function to create a bar chart instead. The histC function has a standard set of optional arguments. With histC, you have options to specify observation weights, the dataset name, the number of digits you want to see after decimal points, and whether you want to print your results to an HTML file in your working directory. The breaks argument isn't a standard option, so I will show you how to use the breaks argument in this video. The histC function generates a histogram plot which you can customize using the main xlab, ylab, and bar.call arguments. By default, histC will generate a histogram plot, but you can suppress it by setting the plot argument to false. To see how to use the histC function, let's work through some examples together. We can use the histC function in the RCPA3's package to create histograms and frequency distribution tables for interval level variables. I want to show you how that's done. Before I started the video capture, I installed the package RCPA3 from CRAN and loaded it using the library command. And to execute the command, I would type its name, lowercase h hist uppercase c, histC, and the one required argument is x, and that is set equal to the variable for which I want a histogram. And to illustrate, I will use the NES variable age, the age of the survey respondents. Give that a run, and it should give me a table and a plot. And I hit return to see the plot. So let's look at this table. The table is captioned distribution of bin values of NES age, and this first column interval specifies the age intervals. So the first interval is including age 15 up to including age 20. And then the next interval is greater than 20 up to and including age 25. Next interval is greater than 25 up to age 30. And you can see the intervals are spaced out at 5 years apiece. And for each interval, I get the frequency of observations, the count of observations in each bin, the percentage, as well as the cumulative percentage. And the histogram, that's the name of the figure over here, shows the frequencies plotted. So our first age item, 15 to 20, has a frequency of 133, and that's the height of the bar of the histogram. You can see the overall distribution of ages, and there are some issues with this, frankly, that can maybe be addressed with our optional arguments. One, you might note that it goes down to age 15, and there are not respondents age 15 in the NES. It starts at age 18, I believe. The reason for this is the bins are all forced to be equal width and 5 units apiece, 5 years, and so for a bin to end at 20, it must go down to 15, even though there aren't age 15 respondents in the survey. And as we will see shortly, some of these numbers are a bit off because this basic function call of just the required argument age isn't weighting observations appropriately. So I will show you in the next part how to weight observations and make other adjustments to get a slightly better histogram. But I wanted to start with just a basic call of the function to show you how it generates a histogram. We've created a basic frequency distribution table and histogram using the histC functions, one required argument x, and we're looking at the ages of NES respondents. What else can we do with this? The histC function includes a number of optional arguments you can use to refine both the table and the histogram. Some of these should be familiar. For example, W is here, and that argument allows us to specify observation weight, to weight observations, and for a survey like this, make the results more nationally representative. And in this case, you see an interesting result here where the lowest bin, the first 15 to 20-year-old respondents, is low frequency when each response is given equal weight, but when responses are weighted to make them more nationally representative, you see the frequency of very young respondents go up considerably, not as high as the other bins, but comparable. What else can we do? The data tag should look familiar. You can specify the name of the data. Breaks is an important one I'm going to come back to shortly, but we see some other usual suspects like digits to specify the number of digits after the decimal point. freqC to print our table as well as any plot we create to an HTML file in our working directory. We can do that by setting the freqC argument equal to true. Plot allows us to specify whether we want to create the graphic. We could set that to false to suppress the graphic. We can specify the main title of the histogram, the X label of the histogram, the Y label of the histogram, as well as specifying the bar colors if we want something than the default 80 gray color. Let's talk about the breaks argument. That's the one that's unique to the histC function. You won't see in other companion functions. So what's that all about? Well, the breaks are the values that define the bins. Generally in a histogram, the bins are equal width, so like in this case they are all 5 years wide, and that way over across equal bin widths you can see the relative frequency of observations within each bin. This has 11 bins, I believe, as this gets broken up over years, but we can modify this number, raise it or lower it. If we lower it, we'll see it in less detail and see broader patterns in the data. If we increase the number of bins, we'll see it in more detail, but then it can get a bit noisy. So let's take a look. Let's say I want to lower the number of bins, reduce the number of breaks. Let's try a number like 4. If I run this, I do get 4 bins, and as you can see now, they are all 20 years wide. So the first bin goes 0 through 20, although we know that there are no respondents under the age of 18, but we can see that their relative share of that first 20 years, 20 to 40, compare that to 40 to 60, 60 to 80. And depending on our purposes, this histogram might be preferable to the one we saw earlier, or if we thought the earlier histogram didn't give us enough detail, we could increase the number of breaks. Here I'm giving it 20 breaks, but I'm getting, it looks like the same histogram I did initially. Now one note you can find really in the technical details of the histC function and the function it depends on is that the breaks that you suggest or you supply using the breaks argument are really considered more of suggestions than they are commands to the function, because going back to the purpose and the identity of histograms, they're designed to give you equal width bins, and generally the idea is to give nice round numbers. Like in the histogram we're looking at now, it has nice round numbers. They all end in 0, like 20, 30, 40, so it's simple to look at, pleasant on the eyes, intuitive in its format. What if I increase that again? Let's try 30 breaks. Okay, now I get quite a few more breaks. Now, the pros and cons of this, we see more detail in the cases to see where individual 2-year bands, are they all 2 years? Well, this would be 3 years, 18, 19, and 20. So that's why it's taller. So you can see some variation in the years in more detail, but it starts to get noisy and maybe is not showing the broad patterns that we would like to see. And then obviously, like if we were to include a table in a paper or a presentation, I think this table now with bin breaks set to 30 is getting awfully long. I mean, remember the point of the histogram rather than the bar chart was to avoid attempting to have a row or a bar for every single individual year from age 18 to age 80. And with too many breaks, you are approaching the problem of using a bar chart for interval level data. So a bit of trial and error, and then thinking about the purpose of your histogram. What are the essential features? What are you trying to convey, or what are you trying to view? And some of that level of detail, to zoom into the data or zoom out from it to see broader patterns, is controlled by the breaks function. Sorry, the breaks argument.